Give me 1 second. Okay, I really just want to start from here. You can see my screen, right?
Yes.
Sure, okay. So first of all, the first two modules that we plan on is really just focusing on first two chapters, I believe. But specifically, I do want to give you a high-level introduction about the book first. So if we look at this, the first chapter, what we do is really just introduction to optimization. So in here, we kind of one thing I want you to be aware is for in terms of optimization, apparently in the textbook it has some simple explanations such as simple as this, right? So as simple as this, and then but here one thing here I want to mention is really this is a nonlinear optimization. Why it's nonlinear? Just because the function itself is r squared. We're trying to minimize s, which is a nonlinear function of unknowns. Unknown would be the r and h, and then with certain constraints. That's why we consider this to be a nonlinear optimization. And then I think, yeah, I don't know, I didn't pay attention to one of the questions. I think someone was raising this question regarding this to see why this actually is there. I think the reality is just because we call this as one of the constraints, equation 114 as the constraints, and based on the constraints, you can rearrange so that we have h equal to v0 divided by pi r squares. And then we can substitute h into that function so that the s now becomes only a function of v0 and r. So apparently v0 is something that we already know, which is 10. So that in order to solve for this s, we want to minimize this s. It's just a quadratic function that we need to quadratic plus 1 over r, this kind of function that we need to minimize, right? In order to minimize this, usually if you recall, when we have the quadratic function when we want to solve, it's really just trying to do one thing that is I'm just trying to get a pen somewhere. Yep. So essentially, if in the here is something like this, right? When we want to minimize to find where the minimization is, the best solution that we usually try to do is just take the first order derivative. So that's how we can find the solution. So and then if we continue here, it's really just that. Like if you just continue, you would be able to solve. The key point here I really want to see is here is a general formalization, right? So basically we have a maximize or minimize with objective function. This is called objective function with certain constraints. And then depending on whether this function is linear or nonlinear, they have multiple branches of optimization. One of the branch is called linear programming. Linear programming is basically saying everything here is going to be linear. For example, I do want to give you an example. Let's see, do we have it here? I don't think so. So that's linear programming, but let me still share share a whiteboard so that I can quickly give you an explanation of what exactly is linear programming. Hang on.
Professor,
Yep.
in the end of the first chapter of the book,
Right.
it talks about different additional methods for solving highly nonlinear multimodal problems.
Right.
Are those generally the types of problems that are going to be encountered in different data science algorithms or models?
Um, let's actually hold on to that question. Once I get there, we can discuss a little bit there too. Here, I
Okay.
really just want to at least start. You can see my whiteboard here, right?
Yeah.
Yeah, so here I really want to introduce the concept of what we call it linear programming, right? So linear programming, so I give you an example. So suppose that if we see that x1 is suppose in I think we do have some examples, I believe, did we? Suppose that we have example says, okay, there's specific manufacturer that they're trying to maximize their profit of making chairs and tables. That's a simple example. It said that question is how many chairs they should be manufactured and how many tables that they should manufacture. So if this is the tables, x2 is the tables and x1 is the chairs, right? And then we know that each chair can be sold for $5, for example. So that we say, okay, $5 of each chair. If I manufacture x1 units of chair, then I'm getting 5x1. And then on the other end, if I manufacture x2 number of tables, then assume each table is $20. Then that would be my objective function. I say that, okay, that's my maximize. I'm trying to maximize this. And then it do have some constraints subject to, for example, usually two types of constraint in this example. One type would be say that we only have limited resources such as the lumber, right? So in that case, we say, okay, I only have 20 square footage of lumber available. In that case, then I say, okay, each of the chair probably needs, I don't know exactly how much it needs. Let's assume it's just 1 unit of the lumber, 1 square foot, for example. Let's use 2. So 2 square foot. But the table you have to probably use, let's say, 6, right? 6 units of lumber. And then in this case, okay, 2x1 plus 6x2 has to be less than or equal to 20. That's my constraints, right? So that's one of my constraints. Second constraint says, okay, I have limited labor. So each of the table takes 10 unit of the labor, and each of the chair probably consumes. Let me just mute some of you. Oh, okay. So maybe, okay, in that case, okay, each of the chair maybe just need 3 units of labor, man hours, for example, right? So in that case, we also say, okay, I only have 2 workers and I can only spend 100 hours for those 2 workers, for example, right? So that would be my constraints. Apparently, we would say x1 larger than or equal to 0, x2 larger than or equal to 0, right? So that would be my constraints. And in that case, here, this particular question here is something we called linear programming. Why it's linear? Because this is all linear. If you look at the example that I showed you earlier, it says r squared plus something over r. Apparently, this is nonlinear just because it has this 1 over r and also has a square, right? So this is called linear programming. And then how to solve linear programming? Something called simplex method. But in this case, I'm not really trying to introduce this exactly, but one thing you should be aware, graphically you should be able to solve it. For example, what is this line? 2x1 plus 6x2 is going to be less than or equal to 20. When x1 is 10, then it would intersect, right? So that's 2x x1, x2. So in this case, it should interact here, and also x2 should be equal to intercept should be somewhere around 3, right? 3 point something. 3 point something. Let's call it 3.3 or something, right? So if that's the case, remember 2x1 plus 6x2 is really equal to 20. If it's equal to 20, it's really just a line, right? It's just this line that I just have. And then we said, okay, 2x1 plus 6x2 should be less than or equal to 20. So everything that's more like in this area, anything on this direction, that's my area. That's my area. Anything in this direction, right? Okay. And then of course we have this says, okay, x1 larger than 0, x2 larger than 0, so that essentially we do not even have anything here. Let me try to erase that. So we kind of know. Oops. I kind of know. Let me get my pen back. Mm. Mm. Now it's back. So let me just still go back to that graph, right? So if that's the case, then really what we're talking about is really just this area, right? Go ahead.
We don't have my
What?
Start crying.
What? Oh, I can't hear you. Can you say that again? Oh, you're probably talking to someone else, right? Okay, so that would be one constraint. How about second one? Similarly, we have this 2x1 plus 10x2 less than or equal to 100. Let's use 100 first, so that x1 is somewhere at 33. So this is really not a very good example, but really what I want to see is, I'm saying it's not a very good example because potentially that line is where, let's see, somewhere here. So let's call this the 33. And this is 10, right? Somewhere there. So that's a new line. But we said it should be less than this as well. So there's a chance that essentially the overlapping area is only here. This is my feasible region. This is my something called feasible region because this is where the potential solution could be in, right? It's feasible region. And then let's look at this function, which is the objective function. What is the objective function? If we have y equal to 5x1 plus 20x2, sorry, x1 plus 20x2, what is that line? Is potentially would be some sort of, depending on the slope, some sort of function like this, right? The function should be a bunch of parallel lines. And we said your solution can only stay here. And then you're trying to maximize that. And this direction is decreasing. Essentially, that's why potentially, if indeed this set of parallel lines are the objective function, then this potentially would be our optimal solution. Right? That makes sense. Any questions? This is called linear programming. Okay. If no questions here, another thing is, of course, here we said x1 larger than equal to 0, x2 larger than equal to 0. But what if we say that, okay, you can have a fraction number of chairs. You can have a fraction number of tables. In that case, we say, okay, x1 and x2 has to be integers. Essentially, we come back with a new set of constraints. x1 and x2 has to be integers essentially means what? It means that what we just have there would be a little bit different as well, right? This is no longer the feasible region. What is okay? This is no longer the feasible region. The feasible region, other than those that we just had, is really that it's really that just this lattice of points, because it can no longer take fractions, right? It has to be just, if this is 1, this is 1, 2, 3, so on and so forth, right? So in this case, now you can only take integer solutions. For integer solutions, it does have its own family of methods that can solve this problem. So in this case, we call it, instead of LP, linear programming, now we call it IP, which is integer programming. Integer programming. For integer programming, it does have its own solution methodology. Okay, so now if I actually introduce you two things, right? LP and IP. Third thing is really what we call it NLP, which is nonlinear programming, which essentially is what we had in the textbook. Now let me share this back. Screen 2, right? So now in this case, 1.22, you can see here, we say this is general formulation, and the reality is we actually continued with a lot of nonlinear function. See here, it's nonlinear function x squared and exponential of negative x squares. And then here, anything that you saw so far in these examples are really just nonlinear optimization type of solution methodology, right? So it didn't really touch upon linear programming, specifically go back to nonlinear programming. One of the reasons is, as you can imagine, a lot of the questions potentially would be nonlinear. And for nonlinear programming, if we go back to the question that you just had, these potentially would be the, for example, penalty method is the method for one of the method for solving nonlinear programming, and Lagrange multiplier is another methodology, which apparently if you reviewed my video, you probably already know. And also this KKT conditions. And then you were asking, your question specifically were asking about this.
Yeah, I guess I just wanted to know, since the
Yeah.
book skipped over the simpler optimization, do most applied optimization algorithms that models use in data science, are they all in by and large nonlinear?
Yes, yes, for your question, to answer your question, that's correct, because if later on, once we continue with some of the problems, for example, apparently this chapter 1 is really an introduction, right? And then chapter 2 give you a little bit background on math so that with the hope that starting from chapter 3, you would be able to give you a little bit more math foundation, and the chapter 3 give you more detail of optimization method. And here, some of this majority of these questions that we're dealing with here in this textbook is really just nonlinear optimization. Now in chapter 4, once you get into chapter 4, even just for regression, which you already most likely know, which is, we know it's least squares, right? Trying to minimize the, let's say, linear regression, trying to minimize the, this is if it's parametric, but how about, how about the just linear regression itself? It's really just trying to minimize the mean squared error, right? So mean squared error, which is at that point you probably would know. So that's linear regression. And then even later on in some other methodologies, you would realize a lot of this, like support vector machines, as well as neural networks, they're really just nonlinear optimization type of problems. Essentially says that a lot of the data mining, machine learning type of problems are indeed nonlinear optimization. It's really more or less like this, in my opinion. Does it help to know all of this math? I guess yes. But in reality, when you really run a specific algorithm, you probably just run a code and get the results. However, I think when you try to get to this level of understanding, you can always know deeper on the subject. And then eventually, when you when you're trying to explore some other new topics, you can use this methodology as a starting point to understand the problem definition, things in that nature. So essentially, all that I want to say is some of these data mining techniques would be nonlinear optimization as well. Yeah, that's correct. So what you just said is a long answer to your short question. Yeah.
On that note, is there based on the model and the actual specific formulation of a problem you're working on, are you going to choose? Is it possible that you're going to choose a different type of model because it is computationally more effective for the specific problem? Is the underlying understanding of the optimization going to play a role sometimes at that point?
I would think so, because eventually you should know what's the advantage and disadvantage of each methodology brings. So that advantage and disadvantage is really potentially could be coming from the math formulation itself. So I don't know how much linear regression you guys have in terms of exposure at this point of time. Just come across something I'm just thinking about. Let me show you. Again, I'm just trying to get a whiteboard. So let me clear all of this. So for linear programming, what we said was we are trying to do one thing, that is minimize mean squared error, right? And then if you recall anything, have you studied ridge regression kind of thing topic?
I don't believe I personally have yet.
No, ridge regression and something called lasso regression.
Oh yeah, lasso. So you're talking about adding a penalty.
Exactly. Yeah.
Yeah. I've used lasso.
Yeah. Ridge regression and lasso regression is something that's a variation of linear regression. So linear regression, if you recall, what we're trying to minimize is a summation of I from 1 to n for all the observations yi estimate minus yi squares, mean squared error, right? What's your estimate? What's your observation? Squares. Now we know that yi hat can be something as simple as, because based on the formulation, we say it should be equal to, let's call it beta 0 plus beta 1, x1 plus x2, beta 2, x2, etc. And then we say, okay, once we have this, we can put this in there. Then the objective function itself is minimizing beta 0 plus beta 1 x1.
So doesn't that beg the question, why do we square the error? Because that is what's taking it from a linear programming problem to a nonlinear programming problem.
That's so why do we square? That's a more or less there's some deeper mathematics behind that. We were saying that let me think. Really mathematics is really this, because when we did the linear regression, these are the observations that I have. These are scatter points, right? And then if you recall, we're really trying to figure out where is the line. The question is really why it's this green line looks fitting better rather than the blue or red, right? So question is why? Why is that? And then the reason that we choose this square is just because the distance between your, for specific x observation, your corresponding prediction from the green line is really, let's use this x because it's clearer here. It's really here, right here, if you use that green line. But your observed value is really here. So this is a distance. This really is a vertical distance. And then we said we are trying to minimize square of this. One of the main reasons is because some of this could be negative right here. Some of them can be positive.
So you're only squaring the error so that you're minimizing absolute distance.
Exactly. That's the reason. Because otherwise, potentially if I cancel some of this, it's just not going to work.
Isn't it also because you're penalizing this by squaring it acts as a penalty function against outliers? So things that are
not really, because you're penalizing some outliers, for example, right here. But that's really not the main reason. You're not penalizing, because if you are penalizing here, if these are the outliers, for example, right, looks weird, odd from the original data, imagine that your output should probably look like this. You are not penalizing because you're actually trying to fit these outliers, right? So
maybe I misspoke. Your outliers are given more weight in the model.
Given more weight in this case, that's true. That's true, but in order to deal with these outliers, there are some other ways, right? It's not really, you can't really try to solve this by helping to give them, the ways is really trying to give less weight here so that we are able to figure out this green line rather than the other ones you probably already know previously. Right. Okay. So Yeah, and the next thing that I really continue here, if we just continue our thought process, this is our objective function mean squared error, and then we penalize for ridge and lasso. It's really just that the objective function add two terms. One term is summation of beta I absolute value from I1 to n, for example. The other term is really summation of beta I squares I equal to 1 to n. So imagine what happens here. By the way, this absolute value is really just this lasso regression, and this is the ridge regression. So if you have both of those two terms, there's a separate name. It's called elastic net. Elastic net. And then you could have weight for those two terms, right? I call it alpha 1 or alpha 2. As long as I can define alpha 1 plus alpha 2 equal to 1, so that I can make a decision on it's a lasso, it's a ridge, or it's a combination of both, which is called elastic net, right? So alpha 1, if alpha, essentially, if alpha 1 equal to 1, and alpha 2 equal to 0, if that happens, it's really just the lasso, as I just mentioned. But if alpha 1 equal to 0, but alpha 2 equal to 1, then it's going to be the ridge. So this is why I say, okay, I can as simple as just use alpha 1 or 2, and with this definition, if it's not 1 or 0, then it's a combination, which is called elastic net. So the reason here, I'm giving you maybe a little bit too deeper of this, but all what I want to say is just because of these terms, you kind of expect the lasso and ridge potentially would be doing something different in terms of penalizing the beta. So what's the purpose of penalizing this beta? If you recall, it's really trying to, if you think about this, right? This is my objective function now, plus a beta term, right? Together, what would happen? Sum of the beta will become 0. Because I'm penalizing this alpha and beta, alpha 1 times summation of beta. So sum of the beta would be 0, so that this would be minimized. On top of that, we have this function, this part as well, right? So that's why the reason that we add these penalty terms is trying to drive sum of the betas to 0. Drive sum of the betas to 0 so that we get a simpler model. What's the purpose of a simpler model? It's probably too much at this point of time, but let me continue here actually. What's the purpose of a simpler model in machine learning? X-axis is complexity, if you ever studied this. X-axis is complexity, Y-axis is the residual of the model. Residual, let me call it just residual. Complexity of the model. As the model becomes more complex, your residual, your error should come down. However, just because the fact that the model becomes more complex, there's a chance that your model is going to what we call overfitting, right? Overfitting. You fit in too well to your data. You fit in too well to your data, running the risk that it's going to overfit the data. If it overfit, then when you have new data, you potentially could be, let me use a different color, you would be generating more error on the new data. Let's call this new data. So this is something called bias and variance trade-off. Bias and variance trade-off. So we don't really want our model too complex. The model should be able to be simple enough and will be able to deal with new data. So we're really looking for a model that's going to be a combination of those two lines somewhere here. So I'll provide you some more reading after class, but here, that's why it's going to be, that goes back to what I said. For linear regression, when we add the penalty terms, we're looking for a simpler model to drive some of the betas to 0 so that the model is going to be somewhere here rather than very complex, right? So if you think about, okay, people talk about neural networks all the time, deep learning, it's running the risk of being too complex. Definitely running the risk. Of course, there are some ways to deal with it, and hopefully, in your data science exploration in this master program, you would be able to get more exposure and deeper understanding of all of these concepts. Okay, so actually I use the really trying to answer a short answer, use a long answer to answer your short questions. So my point here is, for linear regression, if we add a penalty term with that lasso term or the ridge term, there is a reason for that. The purpose is trying to make a simpler model. So, and then question becomes, if you want to make sure that your model have this feature, you do want to add that penalty term. In other words, different mathematical formulation give you different perspectives. Yeah, I think that's really the summary of my answer to your question. Any other thoughts actually before we kind of, yeah, I think that's really, I hope that I did a good job in terms of explaining some of these concepts, but really it's a little bit beyond what we kind of trying to cover here. But I still think that it's important for you to at least get perspective where we are, why we're kind of going through this. I actually kind of like this textbook. One of the reasons is because it gives you more deeper understanding of data mining, mathematics behind deep mining, right? Algorithms for data mining and machine learning, rather than, oh, you know how to run a linear regression, but you don't know what's the formulation behind it. Let me see. I also want to bring up the cost side. Yeah. So I'll provide you a little bit extra reading after today. It's really not for helping you to understand this material, but helping you to understand what I discussed today for linear programming, integer programming, and as well as linear regression and bias and variance trade-off kind of concepts. Because eventually all of this you should be able to know after you finish the master program. I think this is important because otherwise, if you see a graduate here, if someone asking you some of this underlying kind of understanding, you should be able to kind of tell them what's going on. Yeah. So without too much of let's look at here. The one spend a little bit time on the syllabus. Yeah, So here, if you read carefully, what we really want to do is just to understand major data mining machine learning algorithm from optimization perspective. To formulate this optimization problem, to understand how you can know what would be the solution, right? Learn how to use optimization tools. Yeah, I think this is really the key moments. Some of this is really not too much relevant. We're hoping that, you know, eventually all of the data sciences courses would help you with this. But key for here is really this.
Professor,
Yep.
when you discuss learn optimization tools, are we supposed to use that for the homework assignments, or are we supposed to do that by hand with
It's really just the programming language in R, in Python, how you solve a optimization problem, right? So solve the nonlinear optimization, for example, right? So, for example, apparently, if you look at the textbook, it do have a lot of math details, but some of the questions, homework-wise, some of them I'm actually asking you to use math, which is more or less replicate of what we saw in the examples in the textbook. But some other questions would be using coding to solve certain problems. The combination of both, obviously.
right? So for the first week's assignment, we're supposed to, you know, do the derivatives and all that by hand, but later on in the program, there'll be actual coding examples.
That's true. Yeah.
Gotcha. Okay.
That's true.
thanks.
Yeah. And then here, in general, you know, yeah, I do have clear kind of laid out so you know what to read, right? I think this is actually, this is not correct. This is actually done by, this is not correct. I think this is actually 1 week behind. 1 week behind, right? Because we started last week. So the first week homework should be due on the 7th. Let me see, actually, I could be wrong because I don't remember how I set it up. So let's see. Do you remember when is the homework one due? Is this weekend or next week? Yeah, here I think it's February 5th, right? Yeah, February 5th. So here I should actually revise the syllabus a little bit. It's 1 week behind. This is not right. It should be really Feb 5th. And the next one is really Feb, 2 weeks from Feb 5th, which is going to be February 19th. All right, so I'll revise this and re-upload here, but looks like the coursework, I mean the Blackboard is set up correctly. So follow the Blackboard rather than the syllabus. I'll revise the syllabus and provide an updated version in this folder. So that's the second thing I want to discuss. That's really it, actually. And then if you look at all of this, as I mentioned, right, introduction, some math foundations, and then optimization algorithms. After that, we continue with a couple of the data mining methodology, different directions. Of course, you know, each one of this is more like an introduction, but from an optimization perspective. And then if you started learning some of this in further depth in any of the other courses, I'm pretty sure they're providing different perspective rather than the perspective that we are able to provide here in this class. Any questions? Okay, so see, you can see that I'm now trying to replicate what I have in those videos because I think that would be not the best usage of our time. I just want to kind of maybe next time if I have some slides, I'll show you as well. But at least give you a perspective what kind of things potentially I'm envisioning for our like every 2-week type of meeting. And I also hope that the reason I've set this to the second week is because I hope that you would be able to read the textbook in the first week. And in the second week, when you come into our class on Tuesdays, sorry, it should be Tuesday, just today, this week is a kind of accident. So it will be Tuesday and at 8 p.m. And I expect that you read the textbook and also review my videos already and come with maybe also preview the homework and come with any questions you may have. And then I can think of some topics potentially I think is relevant and talk about those as well.
Professor, I do have one question from this week's reading.
Yep.
I understood the example with one variable when it came to the second derivative test for the minimum or maximum, but when it came to the Hessian matrix, I didn't understand the equivalent test there exactly.
Let's see here. Okay, I see. So let me actually show you a whiteboard again. So now you know I have an objective function max half, for example, x minus 2 squares plus 30, for example, right? Apparently this is a math question, right? It's really what we call here, we say this is a quadratic programming problem because it's x squares. And then we can take first order derivative, let's call it this O, right? I call it objective, that's O. So I can take O with x and then set equal to 0. And then I would be able to find where that x is. And then the second order derivative larger than 0 is really telling me that this is going to be less than 0 because we're talking about a maximization problem, right? Because we're talking about maximization, so it has to be less than 0 so that we know this x is indeed our maximum, which essentially is something like this. A quadratic function looks like this, trying to figure out where that x is, corresponding x. That's just one dimension, one variable. And then how about 2-dimension? When you have x1, is actually using linear regression as that example again, which is, yeah, maybe not necessarily linear regression. But let's say, let's use linear regression, for example. When we have y equal to beta 0 plus beta 1 x1. So in this case, our objective function becomes beta 0 plus beta 1 x1 plus beta 2 x2 squares. This is my projection, right? Minus, this is my y hat, minus yi, the actual observation, squares. When we have this, now we have 2 parameters. One of them is beta 1, second one is beta 2. That's why we need this Hessian matrix. Hessian matrix is something like this. This, again, I call it O, right? That Hessian matrix is objective function first order derivative in terms of beta 1 and do this again with beta 2. So because we did that twice, that's why you should have this. And then this is diagonal, right? The diagonal is also on this side is the same. And the off diagonals would be this objective function in terms of beta 1 twice. Beta 1 did do this partial order derivative twice on beta 1. And here, same thing, partial order derivative in terms of beta 2 twice. Now, this is called Hessian matrix. So if you kind of get it, which essentially is just because it's multivariate, it's not just one x, right? It's different from what we say earlier, a half x minus 2 squared. We only have one x. But here you really have two parameters, beta 1, beta 2. That's one Hessian matrix become handy. Instead of doing second order derivatives, now you have to do second order derivatives in terms of the first parameter, second parameter, as well as first and second. Now this Hessian matrix, in order to make sure that your objective function is indeed optimal, we're saying that a determinant of this Hessian function should be larger than 0, which is essentially equivalent to the second order derivative of x larger than 0 in this example. Of course, earlier I said less than 0 because I was saying that was a max problem, but here you can also consider that to be a minimum problem. So difference between those two you can see only just because of the multivariate nature of this.
So in the book, when it said the Hessian, it said positive definite. That just means that the determinant is greater than 0.
Exactly. Yeah, I'm surprised that it didn't mention that. Let me see. Let's go there. Let me go there. Where is it? Semi-definite. You have to point me to the, because I read the book a while back, not recently. Maybe we can search. Let's see if we can search semi. It didn't come back. Yeah, semi-definite is indeed this absolute value larger than 0. So essentially saying that for Hessian matrix, you can still see the whiteboard, right? Yeah. For Hessian matrix, semi-definite meaning this absolute value larger than 0. Yeah, I'll provide you some of this link too, so that you can read it. Yeah.
So you just think of it the same way as a min max, and there could be an equivalent saddle point as well in multiple dimensions.
Exactly. That is the exact reason. That's the exact reason, because we're trying to
what semi-definite means when it's the equivalent of that saddle point.
Semi-definite means this Hessian matrix absolute value should be larger than 0, and this semi-definite is helping us to confirm the first order derivative that figure out beta 1, beta 2 indeed is a saddle point. Yeah, that's a precise way to understand it. Did that make sense?
It's a critical point or a saddle point? Because for one variable, the saddle point is when it's equal to 0.
Right, but when we solve for two parameters, what do? The first thing that we do is still first order derivative. And O beta 2 equal to 0. This is how we're solving for beta 1, beta 2. That's the first step. Second step is this, which is equivalent to this second step here on the right. Do I make sense though?
Yeah.
Right? Because in order to solve that, the first thing you would do is really just first order, not second order. In order to solve that beta 1, beta 0, you're doing the partial derivative in terms of beta 1, in terms of beta 0, beta 2, and set them equal to 0. And solve for beta 1 and beta 2. That's how we get the solution for beta 1 and beta 2, which is usually what we call is the normal equations in linear regression. Right? It's really not anything related to normal distribution or anything, but it's really just purely just this set of equations is something called normal equations.
So so it's how can you tell if it's a min or a max, I guess is what I'm saying, because
we know after we do the first step, setting them equal to 0, we know we find a solution for beta 1, beta 2. Now we're trying to figure out whether it's minimum or maximum. And then we are trying to see, okay, if this is essentially larger than 0, then we know it's going to be a minimum because it's just the same thing as what we saw on here.
oh, I see. And if it's
Right?
less than 0, it's a maximum.
Exactly. Yeah,
Oh,
exactly.
I see.
Yeah.
I understand. Thank you.
Yeah,
Thank you.
exactly. Yeah. But another thing is any question, any optimization problem of the max problem can be rewrite to a minimum problem. Because if you see minus x2 squares maximizing this is equivalent to minimizing the opposite of this, right? Negative of that. So that's why in a lot of programming languages, in R or Python or a lot of things, they only provide a minimization solver. You think you're trying to solve max problem, you just translate to a minimum problem there, as simple as that, right? So that the solver that they develop, they only focus on one type of problem. I think majority of them is a minimization problem. I could be wrong, but don't quote me here, but it's equivalent. So you can do one thing or the other. Okay. Any other questions from you guys? I hope I did do the recording actually. I think I did. Otherwise, yeah, I did. That's great. Yeah. No other questions? Okay, so if no other questions, I'll see you 2 weeks from today, if I remember correctly. Unfortunately, it's actually Valentine's Day. So I may have to push to the Wednesday or Wednesday as well, because it's Valentine's Day on Tuesday. Okay, I'll send out a communication today, actually. Maybe this week sometime, yeah. No other questions? Okay. Feel free to let me know if you have any questions, send me an email or just ask questions in the Blackboard system. I'll try to respond there as well. Okay, I'll see you guys in 2 weeks and on Wednesday.
All right, sounds good. Have a good night.
You too. Bye-bye.
Have a good night.
Yep.
Bye.
Good night. Thank you.